since, I mean, this is a general workshop, I know that there are also people who are not strictly in the field. Maybe I will give first 5 minutes with of general, slightly general introduction, but I will try to give it short. So the main goal of these neural network quantum states, of the ideas that I'm going to tell you about today, is about studying, about introducing variational representations of quantum mechanics. So the idea is pretty old as quantum physics, and stems from this very simple observation. So the idea is that while it's true that a generic quantum state lives in this in a huge, potentially huge state space, which is essentially the Hilbert space where all quantum states live. However, there is a potentially useful, very useful simplification that comes from the fact that we are typically not interested in describing a random state, if you want, in this vast land which is the Hilbert space, but we are interested in preparing both experimentally and theoretically, if you want, for example, ground states of given Hamiltonians, or study the dynamics of a given Hamiltonian, or some time-dependent, if you want, open quantum system. But in general, in this, we believe that these states occupy only a corner, so a much smaller, if you want, portion of the full possible space that can be occupied by a general, let's say, random state. So these states instead have a lot of structure. Okay? And this is at the heart of the variational method, which is as old as quantum mechanics, essentially. And the idea is that you represent now your wave function in terms of something that can depend on thousands, millions of or more parameters. And you try to span this subset of physical systems, possibly by changing, if you want, the variational parameters that I call here W. As you can see here, I just formalizing these in the case of spins. So this is a basis of quantum spins, 1/2, but this is very general. You can think that these are just amplitudes of your wave function that you parameterize in the way that you like. Okay? So this is the idea of the variational method. And that's where, if you want, high-dimensional representations in terms of neural networks are extremely useful. And that's what I call neural network quantum states that we introduced already a few years ago. And the main idea, it's fairly simple after all, so is that you describe these amplitudes. So again, this is the case of quantum spins, spin 1/2, but again, can be generalized, it has been generalized to other cases. In terms of a neural network, right? So a deep neural network in this case, you've seen a lot of those already in the previous talks, so I will not go too much into the details, but the idea again is that here we are not parameterizing, crucially, for example, force fields, as you've seen in other applications, but we are parameterizing wave function. Right? So we are parameterizing wave function amplitudes, and this can depend on any quantum number that you have, for example, spin projections or positions of your electron, for example. Okay. Now, some general mathematical properties are known. I will just sketch them very quickly. So the first one is the universal approximation theorem. We know that if you make these networks large enough, in principle, you can extend, you can describe an arbitrary high-dimensional functions, provided that there are some very reasonable assumption of smoothness. And the same is true also for wave functions. So if you take a network large enough, in principle, you're able to represent an arbitrary wave function, where large enough can mean, however, even exponentially large. Right? So this is the worst case, of course, that we would like to try to avoid, but this can happen. From a physics point of view, if you want, from a quantum information perspective, which is also interesting in this case, it has been shown that, however, these quantum states based on neural networks can satisfy the area law, the volume law scaling of entanglement, which is particularly useful, for example, if you want to describe dynamics on long times or some critical phases even in a high dimension. So it's nice that these states can describe, they are known to describe at least some volume law states with polynomially many parameters. So this is the key to this statement. And more recently, also again, trying to understand what kind of states we can represent efficiently, where efficient is really the key here, meaning using only a network that is polynomially sized in the number of degrees of freedom. So, for example, in the number of spins or in the number of electrons that you have in the problem. So without using exponentially many parameters, that's the key here. So in this context, very recently we've shown that if you consider, for example, other famous, if you want, states that people have studied in the field of strongly correlated variational representations. So, for example, matrix product states, this famous representation of one-dimensional tensor networks, you can represent an arbitrary MPS with a neural network quantum state that has a size which is polynomial in the number of spins, number of degrees of freedom. And as a consequence, as an indirect consequence of a theorem proved by so a theorem. Okay, now fine. Fine. So essentially, you can show that you can describe also all the ground states of gapped 1D Hamiltonians efficiently. So if you have a gapped 1D Hamiltonian in 1D, you can show that as a consequence of this theorem. So I'm sorry, now I don't remember the person of the theorem, but I'm sure that people in the audience can help me out. But anyways, this is we can show that we can represent any gapped ground state in 1D because of these inclusion relations, if you want, with MPS. And also, we've shown that we can represent an arbitrary approximate tensor network, planar tensor network in 2D. So these are these PEP star that are usually used. The star here stands for the fact that you typically use some approximations to contract them. But if you allow this for these approximations, that you can also represent these efficiently with a neural network ones. Then there is an extra space that you can see here. This comes from the fact that there are these volume law states that in principle you cannot describe with planar tensor networks. So for example, with MPS of PEPs, unless you allow the parameters in these states to be exponentially large. Instead, there are some new volume law states that we can describe also in polynomial. There is an extra region that we still don't know. It's uncharted. There might well be, I would say, other quantum states that are physically relevant, but that we don't know how to describe. We cannot describe efficiently, but this is still very well open from a theoretical, if you want, point of view. Now, again, also to connect a bit to the rest of the machine learning literature. So how do we learn the weights in these networks? Just very briefly, we use the variational principle. So we minimize the expected value of the Hamiltonian over these states. And we just use the famous formulation of Macmillan that allow us to rewrite, if you want, this quantum expectation value in terms of a statistical expectation value over this classical probability distribution psi square. Okay? So this is the main ingredient. We don't have any external data, contrary to, for example, when you try to fit a force field. We have to generate our own data and try to minimize this expected quantity. And we can do so by standard variational Monte Carlo method, if you want, which is very similar to, if you want, learning in some applications of machine learning. And we can compute, for example, efficiently also the gradients. Typically, we use automatic differentiation to compute these gradients efficiently. And again, all these gradients can be written, as it is very well known, in terms of expected values over this distribution psi squared. Just I want to stress that at variance with more standard, let's say, applications of machine learning, a crucial thing that we found particularly convenient is to use what is known in the neural network literature as the natural gradient, and what in the quantum literature is known as the stochastic reconfiguration method by Sandro Sorella. And this is just a way to precondition, if you want, your gradient with the inverse of this matrix here, which is the quantum geometric tensor. So it's this quantity that you can see here, where O are the gradients of your wave function. And this is extremely efficient because it mimics in the variational subspace imaginary time evolution, or if you want, the power method. And typically will converge faster than standard stochastic gradient descent or other methods. And I also would like to stress that in modern implementation, the scaling of this approach is only linear with the number of variational parameters. So we don't really have quadratic scaling methods. We can apply these techniques on clusters of GPUs or for millions of parameters pretty efficiently these days. Now, most of these techniques that I've been discussing so far have been used, I would say, in 80% of the systems that we and many other people have used these techniques on are spin systems. So before moving to fermions, which is the rest, the 20% of the other applications, I guess, I want to maybe just do a small recap on the state of the art there, just to tell you also how far we've gone there and what is left, if you want, in terms of improvements. And a systematic benchmark that people have used to study the progress on, to assess the progress on spins has been for historical reasons, I don't know, but because people like these models, has been the two-dimensional J1, J2 model. So this is a simple sign problematic model that is hard enough to be not exactly solvable with quantum Monte Carlo and not exactly solvable by TensorNet. So here, essentially, the question, as you know, is whether there is a spin liquid phase, for example, that intervenes between these two orders, extreme phases that appear when J1 is large or when J2 is large. Okay? And now, I mean, on this model, starting from the Heisenberg limit, so where we take J2 actually equal to 0, we've seen a lot of progress. So this is, of course, a limit that we know how to solve exactly with standard quantum Monte Carlo. So in that case, we know the exact energy, if you want, so we can use it already as a first benchmark. So in that case, starting from the first results that we obtained in 2016, the things have significantly improved. And I would say, thanks to many refinements, I guess that also Juan will tell you about this. But this is what I plot here as the error on the energy. And you can see, so these were the first errors that we got using very shallow networks. So essentially, we've learned how to use deeper and deeper network more efficiently. And also the most significant advancement in the field, I would say, has been also this idea of using exact sampling that I think also Juan will tell you about later. So you can see that by using these deeper networks, so this is a much deeper network than this one, we can go from some 10 to the minus 3 error on the energy to essentially 10 to the minus 5, which is to all purposes all you need to study also other properties pretty precisely on this model. The situation on the frustrated case, so in the case when you add a J2 term, so where you turn on the sign problem, if you want, in the problem around 2019 was this one. So here I'm showing the difference in energy between the convolutional neural network results that we obtain with some fairly deep, but not so deep neural network in 2019, and other variational methods that were available at the time as a reference. So you see that if these points are in the upper part of this diagram, means that somehow the NQS energy, so the neural quantum state energies, are lower, so let's say better. Or if they are here, means that there are some other techniques, notably the MRG here, that can have a lower energy. And you can see that, I mean, we spend a lot of time in understanding and trying to improve, especially around this region, which was disappointingly not at the level of the MRG. As of 2021, also that point has finally been improved to the point where it's now by neural networks is the state of the art. This is work by Nomura and Dimada. It's not the work of my group, but I just wanted to highlight the fact that in these recent years there's been a steady progress on spin models. And by now, I would claim that also on these frustrated spins, neural networks are essentially the state of the art for the simplest sign problematic, if you want, spin problems that you have in 2 dimensions. So the main trick that they used here to improve on our original CNN results that you can see here, that were relatively higher than this one that they got at the end, is essentially the idea of combining symmetries and these neural network representations more efficiently. So they take linear combinations of non-symmetrized, if you want, wave function. So they first break the symmetry and then they represent the symmetry after having optimized, if you want, the wave function. And this really improves, for reasons that are still fairly not so clearly understood, I would say, but it's pretty interesting that this happens. They find really significantly better results than what we could with by imposing instead translational symmetry from the beginning using a convolutional network. So this is the state for spins. But as I was promising, what we would like to do is to move to the rest of the applications, which for mostly historical, let's say, reasons have not been so well developed, and these are fermions, and it's certainly something that we are trying to work on more and more these days. And you've already seen the talk by Brian, for example, that told you about some of the progress in that field. So there are many different ways of doing fermions with neural networks. I will tell you the first one, which is just in chronological order, the first that we introduced in this business, essentially. What we did was to map fermions onto spins. So this is a very straightforward idea. So if we have a technique that works for spins, so why don't we just use the same kind of methods also to study fermions directly? And as you know, you can do that pretty easily. So for example, you can do the famous Jordan-Wigner mapping that allows you to map an arbitrary fermionic quantum chemistry, if you want, Hamiltonian onto spin degrees of freedom. This is a very simple mapping. Or there are more complex mappings that are less known in condensed matter or even in quantum chemistry. One of these is the Bravik-Hitaev mapping, they all, if you want, achieve the same goal, which is to map fermionic degrees of freedom onto spins. So, for example, the Jordan-Wigner, which is the most well-known, allows you to map creator or destruction operator C onto sigma minus times this product of sigma Z operators that take into account if you want, the commutation, the anti-commutation relations of the original fermionic operators. So this mapping is completely general, can be done in arbitrary dimension, and you get a resulting spin Hamiltonian, which features, however, these very long-range spin-spin interactions that come from these strings. The less well-known mapping is due to Bravik-Hitaev and Hitaev. I will not go into the details of how this mapping works because it's slightly more, significantly more involved than the Jordan-Wigner one. But the idea is that you also map these C and C dagger operators into something that resembles a sigma plus or a sigma minus operator, but in the middle, as you can see, you insert some other operators A and B, and these other operators A and B are products of sigma X and sigma Z operators. And the interest of doing this is because you can limit, if you want, the support of these operators in a way that you don't have these very long strings as you have instead in the Jordan-Wigner case that can be extensively long, so like the number of spins or number of fermions. But instead, in this case, on average, this thing will have log n length because you use a sort of tree-like representations of the permutation size. So you make the Hamiltonian a bit more local or quasi-local, if you want, than the original transformation that is more commonly adopted, if you want. Now, we've used this approach with very shallow networks. These are early results that we obtained in this, if you want, introduction to chemistry. These were done on, very small basis sets that you can see here on a couple of diatomic molecules. The results that we obtained with the RBM, so these very shallow neural networks, are in green. So these points here, the stars that you can see zoomed here, and you can see that these typically manage on these small basis sets to reproduce pretty accurately the full CI calculations. And you also describe, for example, the dissociation at very large separation pretty nicely. And this was, again, just first entry point into chemistry that was allowed thanks to this, straightforward mapping onto spins. This mapping, however, has some limitations that are especially evident, I would say, when you try to study periodic systems. So, and this brings me to the second way, if you want, to do fermions, which is doing first quantization. So first quantization in this context means, so first of all, what is the model that we'd like to study? So the model that we study specifically is this, it's a periodic system on a lattice now. So I don't have now, if you want, a quantum chemistry basis, but I have a lattice. And I have spinous fermions hopping on a square lattice, and I have some nearest neighbors interactions, density-density interaction. Okay, so this is also a relatively simple model of fermions in 2D, still not exactly solvable in general. And so, as I was mentioning, anticipating the kind of transformations that we can do also, transforming spins, fermions onto spins, can be in principle done also for on the lattice. However, one issue that is slightly annoying is that, as I was anticipating, the Hamiltonian that you get in the spin language is extremely non-local, so you have very long-range interactions. And the resulting Hamiltonian also breaks translational symmetry and other of the interesting symmetries that the original fermionic Hamiltonian has. Okay? Indeed, the problem is that the ideal transformation should preserve locality. However, there is no known transformation between spin and fermions and spins that preserves locality exactly. So locality means that, again, I have exactly all the symmetries of the original Hamiltonian also in the spin Hamiltonian. Unless you introduce extra degrees of freedom, so for example, by mapping things to Majoranas. However, there are extra complications, as we've found out recently also in this variational study with Jan de Snis, and it's not easy to satisfy the gauge conditions that are introduced by these extra degrees of freedom. So if you want, you can have a look at this paper here. So what can we go around this limitation? Well, we go back to first quantization. So instead of working with occupation number, we now work with particle positions. If you want R, I have now an electrons hopping on discrete, if you want, positions on a lattice. And the price we have to pay is that we have to make the wave function antisymmetric, right? So by hand now. So to make the wave function antisymmetric, we resort to a standard trick, if you want, in the community, that was actually historically the first application of neural network quantum states to fermions in this paper by Imada and co-workers. So the idea is that you take a determinant of some orbitals that you keep as free, just free parameters, and then you multiply everything by a symmetric function that you can make also invariant under translation. So symmetric means that depends now only on the occupation number. So this is easy to do on a lattice. And you can also multiply this. So this can be taken to be, for example, positive. And then you multiply everything also by a sort of sign function that is also, and both these functions are parameterized by neural networks. Okay, so this is a positive, if you want, the equivalent of a generic many-body Jastrow factor. And this is a sign factor that doesn't have a strict equivalent maybe in terms of Jastrow, but that can change sign at will. Okay? So we can change the sign of the wave function at will. And then this is maybe not too important, it's somehow a technical detail, but we can use also this kind of recurrent neural network with residual blocks to represent both the sign and this Jastrow-like permutationally invariant correlators that we have in the wave function. So this model is kind of it's not a spectacular physics, but is still pretty interesting because if you change the doping and you change V, it was expected both from Artifoc and some early PEPS calculations that you would find both a metallic phase and some, if you want, a charge density wave at alpha-filling, or quarter-filling actually in this case, and also a phase separation, if you want, in between, sort of coexistence of phases where you have this phase-separated metal with and charge density wave. So in order to study the existence of these phases, we've chosen some order parameter. It's not too important in this context, but just wanted to mention that we take the power spectrum of the density distribution. So if you have a peak at a finite Q, this typically tells you that you have also a charge density wave, or you can also distinguish between a phase separated and a purely if you want, the charge density wave phase by the value of this order parameter, that we can also extrapolate to the thermodynamic limit by scaling, if you want, standard, more or less, side scaling. The phase diagram that we find here is in agreement. So we find the same phases that we were already found by IPAPs, for example, but with some slight change in the actual lines of transition lines, if you want, that are not as spectacular. But we have some quantitative change, especially in large occupation numbers or small occupation numbers because of particle symmetry that you can see here. So you can see that there is a change with respect to the PEPS lines and some change, and also a clear change instead with respect to the RT fog that tends to underestimate, if you want, the transition. Great. So this was just to show you that we can do phase diagrams. Also in these Fermionic models. Now, this was the second approach. There is a third approach that will be discussed in much more detail, if you want, by other speakers during this conference. So I will just keep this discussion on this third approach relatively light. And the idea is pretty straightforward, just to use these same ideas. So first quantization of neural network representation, if you want, but in continuous space, right? So if you want, we forget about now the limitations or the feature of living on a lattice, and instead we allow our electrons to operate freely in continuous space, right? And you've seen already specifically in the talk yesterday by Brian Clark, that the main idea there is to use a backflow now parameterization of the orbitals. Actually, Brian did it on the lattice, but the more recent applications that have been done and you will hear about are for chemistry. This is a rather powerful idea. Just would like to mention that very similar in spirit idea was already discussed in this paper by Marcus Holtzman, Saverio Moroni, and Ruggeri, even though with a very different language. But these two are strictly related. This is, again, a very powerful idea that allows you to change nodal structure. So if you want to go beyond also this limitation that we have here, where we couldn't change the nodes directly, but only indirectly through this sine function here. And this is extremely important, especially on a continuum rather than on the lattice. The only thing that I wanted to mention, because I find pretty telling about the flexibility of neural networks, is that we've used these kind of first quantized approaches for the moment, not for chemistry, but for applications in nuclear matter, where, as you know, there are strong similarities, if you want, in terms of historical similarity, in terms of many body methods that people have used in quantum Monte Carlo, for example. And indeed, it turns out that if you use this kind of first quantized wave functions based on neural networks to study also nuclear matter, we can get also pretty accurate results. So specifically in this work, we were taking a Slater determinant that in this case didn't have a backflow transformation, but that's was the first study we did. And then we parameterized this, if you want, the Jastrow-like, again, parameter here, U, that is taken to be positive with a deep set architecture, which is permutationally invariant on the continuum, that maybe you will hear about in the future talks. And also we parameterize this sign factor with this function here that can also change sign, because this tangent can also go between -1 and +1. And in this case, you can reproduce pretty nicely, for example, the density profile of nuclear density for up to helium-4, and you reproduce also the results that you can obtain with the Green's function, for example, in this case. So these are still at the level of reproducing this function Monte Carlo, but I think it's nice that with this approach, you can already improve significantly over standard wave functions that people have used in the field, for example, Jastrow, Slater, or similar wave functions. Great. Now, the last approach, which is definitely the one I'm the most excited about, I mean, not because I don't like the ones we discussed so far, but I think that this one is conceptually maybe one of the approaches that really warrants further exploration in much greater detail. Are hidden fermions. For the moment, we've applied this only on lattice models, but it's, as you will see, very general and can be applied also to other kind of systems. And the idea is, in a sense, again, relatively straightforward, but I think pretty powerful. And the idea is to augment, if you want, the Hilbert space we are working with. So instead of having only, if you want, visible fermions, so now I'm going back to second quantization on a lattice. Okay? So instead of having now only, if you want, visible, which in this sense means only physical fermions, and now I augment my Hilbert space with also some hidden extra degrees of freedom. So I will call these extra degrees of freedom D, and these are really fermions that can live in some extra space. I mean, and I take M of them. Okay? Now, the idea is that if my target correlated state that I call, I indicate here just with this circle, with this green circle, can be, in general, you can expect that you can describe this a generic target correlated state. So what I mean by target correlated state is the wave function, let's say, of the Haber model for my n electrons. You can think that while this is a strongly correlated state, maybe if I extend the space of all possible wave functions, then this correlated wave function can be transformed into an uncorrelated wave function. So if you want, will belong to the set of Slater determinants, but in this enlarged space of wave functions. So if you want, if I'm able to construct an extended space of fermions, then I can leave and I can map back now this free fermionic wave function onto the correlated subspace by a mapping that will map the density of my physical particles and onto the density of my virtual, or if you want, auxiliary hidden fermionic part. So just maybe to be more clear from a wave function perspective, I think this is maybe easier to understand. So we can write the wave function of my system, where x now are my physical degrees of freedom, so my visible, if you want, degrees of freedom, in terms of a simple, so in this sense it's a free system, Slater determinant. But in this Slater determinant, I will have, so essentially 4 blocks. So the first block are just standard orbitals that depend only on the positions of my physical particles. And then I will have some extra degrees of freedom, some extra, if you want, virtual orbitals in a sense that are still occupied by my physical particles. But then you see that there are these 2 extra blocks that essentially correspond to the orbitals of my hidden, if you want, fermions, that are evaluated on some positions that are a function now of the visible positions. So in other words, I have a mapping, this f, which is a generic function that maps my fermionic, if you want, the positions of the physical particles onto the positions of these extra orbitals that I'm introducing in this Slater determinant of these extra orbitals. And the main thing that we do here, our main contribution, if you want, in this context, is to represent this function f that performs this mapping with a neural network. Okay? So what we do here is that we represent, if you want, this f function in terms of a neural network that takes my particle positions and we return some other positions. So this is one way of doing it, or on the lattice, actually, it's much easier to just represent these orbitals in terms of the occupation, in terms of the positions of my visible orbit. Now, the application that we did here, of course, we wanted to also get started and have some benchmarks on a relatively well benchmarked model, something that people have studied a lot. So the Haber model, spinful Haber model, and we benchmark on the 4x4 square lattice because we have to start somewhere. So, and you see here results for example, our fielding. and the number of hidden fermions that we take here is 8, whereas we have 16. We are on the 4. Sorry, we have 8 both physical spins. We are at 30 and 8. Sorry, we have 16. Sorry, we have 16 physical fermions, and we have 8 instead hidden fermions. Okay? And so what you can see here is the relative error on the energy compared to some more standard later RBM, if you want, wave functions for different values of U. Don't ask me why we have 7.75 or 3.60, but that's what we have. And you can see that by increasing the number of parameters, so in this direction, you increase the number of parameters in this mapping, you can also systematically, up to a point, reduce the error on the energy. And by increasing further, if you want, also the number of hidden units in the fermions, you can also, in principle at least, reduce this error even further. So you can see also a comparison for in the dot case, and where we used a bit more hidden units, and the results that you can see here are again compared against Slater-Jastrow or even Slater-RBM. So if you want, one of the first applications that were done by IMADA, and you can see that we can improve also quite dramatically, I would say, in the sense that by using symmetries. So these lines here refer to the fact that we can apply a posteriori, for example, C4 or T translation symmetries. So we can, by applying the symmetries, we can even further reduce if you want, the error. And we can also improve on these tensor network results that were obtained with some mixed Monte Carlo sampling method by also in the group of IMADA. Okay, so this was also, you can see the behavior on U, which is pretty nice. Now, just to get back to Brian's talk yesterday, this is the comparison with respect to the backflow, neural network backflow transformation. And you can see now, I don't know if Brian has recent results that I didn't get yesterday because I couldn't follow your talk very closely. But let's say the last published results from Brian, from my understanding, are this one in green. So this is on a ladder, and you can see that there is an improvement over also the backflow transformation by using this hidden fermions approach. Typically, you can see it also for, again, this is 1/8 doping, density of 1/8, and for U equal 8 on a ladder, which is a standard, if you want, a benchmark case also for DMRG. The case that we consider here is with periodic boundaries, but and in this case, we find stripes, so compatibly also with what Shiwei and others have found in this paper with many techniques. And the periodicity of this stripe is lambda equal 8, in this case of 1/8 doping. And you can see if this is true for the PBC case. We, at this point in time, also to be completely transparent, we have still some issues. So this is the equivalent, if you want, in a sense, of this pernicious point in the J1, J2 point that has asked for 2 years of effort or so. But the equivalent, if you want, of that point for us in this point in time are stripes in the PBC OBC case. So where we take, if you want, open boundaries in one direction and periodic in the other direction. So in this case, it turns out that we are competitive, but not, if you want, the state of the art on this model. So, for example, if you see the energies that we have here for these stripes in the case of 8 or 16, these are 4/8 or 4/16. We can compare to the MRG, and you can see that essentially this is something that is affects also the MRG in a sense, but also us. We have some issues in metastability issues in stabilizing the correct type of stripe, if you want, or for example, we have that the outfield stripe tends to dominate, in a sense, the variational landscape of our minimization, and the field stripe instead has to be pinned properly if we really want to find that kind of solution in our variational minimization. So this is a bit unfortunate. It's part of the physics, actually. but it's still something that is more prominent, if you want, or more evident in the case of L equal to 16, where you see that our energies, in this case, are not on the if you want, compatible yet with the lowest DMRG energies. But again, this was the first work we did in Fermions. I believe that there is room for large improvement. Great. So since the time is running out, I will go already to the outlook. I just want to mention that we have a very recent release of NetGet, our open source project, that implements also Fermions, especially in the second quantized formalin. So you are free to try it out. We also have support, more experimental, but it's there for continuous space Hamiltonians. So we would be also happy to hear your feedback. There are many experts in the audience on this topic, and we would like you also to try it out. Why not? I also, want to just mention this outlook that I believe that by now we and many others have established that we can really represent highly entangled states with these neural network representations. There are some issues that we are aware of, that many people are working on. Optimization is certainly one of those, also for spin models. So, for example, if you have models with phases, let's say the JD1, J2 model, or some model where phases, the phase of the wave function can be highly, non-trivial and disordered. In this case, standard optimization techniques don't seem to play very well with this kind of variational landscape. There are ways to alleviate this problem, for example, using symmetries, but still, this is one of the things where most of the work is being done. And then for Fermions, as you've seen, there are, there's a lot of recent activity, and again, you will hear at least 2 or more talks about this in the future during this conference. But I would say that we are still limited to relatively small systems. I'm not saying that we are doing only ED-like systems, because it's not the case, but we are still, trying to push this beyond what, if you want, what we can do with other approaches. But when we can when we can approach, or we can start studying systems that are not so small, for example, in this case, when we have periodic boundaries, we can often or sometimes do better than some existing method at least of some variational method that are in the field of quantum chemistry or nuclear matter, or even for the Haber-Bohm. So I believe that there is really a lot of room for further improvements, and conferences like these are certainly the right venue to discuss about future development. Thank you.